Our first presentation deals with an exciting technology, fulfilling the promise of AI, practical value for CPG. Our presenter is Robert Molnar, Director of WorldQuant Predictive. Robert, the podium is yours.
Thank you, and hi, everyone. Hi, my name is Robert Molnar. Happy to join you. I'm dialing in from Budapest, Hungary. Just briefly of myself, as mentioned, I'm currently a Director of WorldQuant Predictive, which is a technology firm aimed to bring the latest in AI to businesses worldwide using a proprietary mix of technologies pioneered by the quantitative hedge fund business. My background is in applied machine learning, and specifically in the CPG space, helping decision makers accelerate revenue and business performance. I have over 10 years experience in this field across numerous consultancy companies, including McKinsey, and I worked with over a dozen Fortune 500 brands, mainly in US and in Western Europe. Today, we'll be talking about a topic that many of us are hearing all the time and reading articles all the time, which is very loosely defined as AI. And the purpose of this presentation is to demystify it a bit, talk about what is attainable, what is still, let's say, science fiction, and bring it even closer to ground level, talk about use cases, 3 of them in particular that are relevant for CPG companies. I'm going to give you examples of projects implemented at large CPG companies in the US, talk about the approach, methodology, but most importantly, how the end user, the business decision maker, is actually getting value from this. Feel free to jump in at any point if you have time or signal it through the corresponding means. I'm happy to pause. We'll also have section breaks after each of the use cases to answer any questions that might come up. So accordingly, let's jump in. What is AI? We are hearing all kinds of things about it. This is one framework that I particularly like to distinguish between what's called artificial general intelligence and then narrow artificial intelligence. The first one is aspirational. This is what we see in science fiction movies. This is about machines being able to perform general tasks at the level of humans. This means multiple tasks unrelated to each other to be performed by machines, such as playing chess, giving stock trading tips, and identifying cat pictures. This is still aspirational, although rapid advances are being made in this direction. What is real, on the other hand, is something called narrow artificial intelligence. This means that a technological system can perform a single, very well-defined, well-delimited task at the effectiveness or beyond that of humans, meaning that a system can play chess, give stock trading information, or identify cat pictures, but do these things separately. Some common terms that we are also bombarded with, just to get it a bit more down to earth. So whenever we're talking about AI, especially in business context, please remember that we're talking about narrow artificial intelligence, as we mentioned. There are some other terms that are very abundant and that roll under this umbrella term. One is machine learning. And machine learning is basically just a set of algorithms, a set of techniques that enable the artificial intelligence to function, all relying on data. These are basically statistical mathematical approaches that are scaled using technology. And then deep learning, this is the third component, the third widely used term. This is, again, a subset of machine learning that entails a very specific type of algorithms using what's called the multi-layer neural networks. Deep learning is the most advanced type of algorithms out there. It's a classification of algorithms, and it's currently applicable only for a very well-defined subset of use cases. So let's talk about use cases specifically within the consumer goods sector. Here you can see a menu of use cases organized into 4 layers. Like the dark gray lines represent these functional areas. This is an arbitrary grouping, but as we found, it's quite representative of how most companies think about use cases and their functional areas. One main functional area is, of course, marketing. The other is customer management. Third is sales management. And the fourth we call risk management. And the orange dots, as you can see there under the different boxes, represent what are the use cases that we are going to focus on today. There are too many to talk about in detail, so we chose 3 of them because they are probably the most prevalent, in my experience at least. Many, if not all, CPG companies are solving these use cases one way or the other. So the purpose of this presentation is to talk about how the elusive AI approach can actually get you there faster and more effectively. These 3 use cases are advertising spend optimization under the marketing management umbrella. Also here, we're going to talk about price and discount optimization. And then shifting gears to what we call customer management, this is where we're going to look at behavioral segmentation, more specifically talking about customer decision trees. So these are the 3 use cases we're going to look at in depth. We're going to talk about the following things.
Robert, we had a question come in real quickly just now. Is augmented reality, computer vision also an AI use case?
Computer vision and augmented reality, I would separate them. Great question, by the way. So computer vision is definitely a AI use case. It's a very classic application of deep learning, right? The computer vision type of algorithms rely heavily on these very sophisticated deep learning type of algorithms. Now, augmented reality is more of an assembly of systems. A subset of those systems are also enabled by deep learning or machine learning type of algorithms, but I wouldn't put them on the same logical field, if that makes sense. Computer vision, absolutely a very classic AI use case. Augmented reality is more an assembly of systems, subset of which is also AI driven.
Okay, thank you.
Yeah, my pleasure. Great question, by the way. So going back to the use cases for CPG, which is, let's say, less exciting in this sense than computer vision and augmented reality, but it can move the needle, which is very important for growth and even cost reduction. So these are the 5 things we're going to talk about under each use case. The context, we're going to talk about the problems and the approach, the solution that was actually then delivered, brief talk about the methodology, I'm going to demo the actual workflow, and then just briefly, this is technical, talk about data needed, because obviously all of these systems rely heavily on data. Advertising spend optimization. This is a project implemented at Fortune 500 pet food brand. First of all, what is the context? Classical definition, problem, approach, and then impact. The problem is inefficient use of budgets across digital media channels that was causing low ROI of the marketing spend, but also was causing low growth. And low means relative to the market standards and definitely low relative to targets. So what was the approach used here? This is where machine learning algorithms really come in. These are mainly aimed to predict the impact of spend on KPIs. And then on top of that, another class of algorithms can actually find the optimal allocation of budgets across the different media channels to optimize that given budget. And then also some visual interface is needed to actually deliver these insights to the end user. What was the impact in this particular case was a $20 million annual incremental growth from marketing spend, and it also provided a single source of truth for all marketing teams to engage on. The solution really typically has 3 parts, and this is very typical in all AI-enabled systems within the CPG landscape. It really offers 3 things. One is, this is the fundamental, the ability to predict certain KPIs. In this case, as the first box shows you, it's about predicting the ROI and incremental lift of the current investments into different marketing channels. The second one is the ability to simulate This is known as the what-if scenarios, a classic way to actually make machine learning more actionable. By being able to action the underlying predictive model, a business user can simply simulate different events, different scenarios. So what if we increase marketing investment in Facebook versus Google? And what if we do that while there's some external event, let's say inflation actually goes above double digits? Those are simulation capabilities. And then finally, we can optimize. We can optimize the budget across the best performing activities so we can achieve the most growth to our KPI. So predict, simulate, and optimize. These are three things really enabled with the right use of analytics. And then optionally, on the right-hand side, you can see an application that really makes this come to life and makes it actionable for a business user. This is optional, like all the value can be actually created on Google, on spreadsheets or in PowerPoint, but it's much more impactful, obviously, if there's a front-end application on top of it. I'm going to jump through this. There are many approaches to advertising spend optimization. Don't want to talk about all of them, but maybe just give an overview of the underlying methodology and I'm trying to make it as intuitive as possible, although unavoidably it gets technical. The main intuition behind any machine learning models, right, is to capture some kind of phenomena by understanding the relationship between that and other phenomena with which there's a causality effect. In our case, it's always sales or a derivative of that, which can be demand. Let's call it demand, or better yet, sales. Let's stick to the definition of sales. And then the question is, how can we predict sales as a function of all other factors that influence it, including advertising spend, as you can see in the first column. So we want to really capture those events, like these historical advertising spend. But also we want to capture additional factors that also influence sales, such as pricing and promo, assortment, basically the 4 or 5 Ps of your marketing mix, as well as all the external factors like seasonality, competitors, and economic factors, pandemic lately, and basically the list can go on. The better job you do at capturing what drives sales, the better performing your machine learning models are going to be. To make it a bit more practical, we're still in the domain of advertising spend optimization. Really, it's about understanding what are all the marketing channels that are driving sales, right? So this is the pillar where we really want to capture as much detail as possible. The usual suspects here are paid search, display ads, paid social media, search engine optimization, electronic direct mail, just to name others. The hypothesis is that all of these channels affect sales because they influence shoppers through various touch points, and they have a deterministic effect on whether or not they're going to shop. And on the right-hand side, this is where we get even more technical. This is about expressing the relationship between investments, like dollar-wise, into these marketing channels, and the payoff, which is sales that can also be measured in dollars. So you put money in and you put money out, and there are different curves that represent this relationship. On the bottom right-hand side, you have this relationship by different channels, and on the top right, you have the aggregated relationship. And then the idea is to optimize the allocation across the individual channels of your finite given budget so as to optimize the aggregated revenue. So then let's talk about actually the main components of a best-in-class marketing or advertising spend optimization tool, but more generically, let's call it workflow, because even if you don't have a tool, you will need to go through the same steps. On the left-hand side box here are different instruments. In this case, we call them instruments, or the channels of your marketing spend that you're interested in. And here you can see 5 of them defined. Not sure if you can read them, but each of them is really a very specific way to spend your marketing budget. The first one in this case is search terms on dry dog food. Remember, this is a pet food industry example. The second one is the same type of search words, but focusing on the branded types more specifically. And the fifth one is Facebook video ads. Perhaps that's the most obvious. And this list can go on and on, depending how individual companies think about their marketing spend. And then for each of these instruments, you can set the weekly or monthly spend. Here they are at a standard value of $10,000 per week. A month that adds up to $40K. And on the right-hand side might be a bit awkward because there's just a drop-down now in action. This just shows all the different KPIs that can be predicted, right? So the idea is that for every instrument, for a given budget amount, we can predict what is going to be the generated KPI associated to that instrument and only to that instrument. In this case, we're saying that if we spend $40K on this specific group of search terms, on the top row, we're going to get $49,000 back. And in the drop-down is just a mix of all different KPIs that you can access. The machine learning algorithms really don't care what kind of KPIs you want to model, as long as data-wise the model can be constructed. You can not only predict incremental revenue, but for example, you can predict average unique visitors to your website. Moving on. Similarly to being able to predict.
Robert, a question just came in. Do you need a lot of historical data to predict?
Yeah, the short answer is yes, but it depends what we mean by a lot. And actually have prepared one slide at the end of each use case to talk about the data needs. It all starts with data, right? You cannot do machine learning or any type of statistical analysis for that matter without historical data. Each of these use cases has specific data needs, which I'm happy to cover at the end of the section. If that's okay, we have a slide that can convey more information. Going back to the workflow, just to give a sense of this predict, simulate, and optimize capabilities that a good machine learning algorithm can enable. We talked about the prediction. What happens if we spend 10K on a given group of search terms, or we spend 15K on Facebook video, right? Or any other number. This is where not only predictions but simulations occur. And then similarly, we can also optimize, right? Once the predictive models are in place, it's relatively straightforward to do an optimization using a different class of algorithms, where we all need to do is specify what is the KPI we want to maximize and what is the target budget we have. Let's say 50K weekly, and we want to maximize incremental revenue. Hitting a button or running a series of algorithms can give you then the optimal allocation across your individual instruments that give you holistically the best response. And this is a visual illustration of that relationship where each of these response curves represents one particular instrument or channel, however we want to call it, indicating the relationship between spend horizontally and the incremental revenue vertically. And the dots on them indicate what is the local best position of the spend amount that gives you globally the best revenue impact. And on the right-hand side, just different ways to illustrate the same data. This is more of a data visualization exercise. The big idea here is that, yes, with the right machine learning algorithms, you can predict the relationship between your spend and your outcome. You can simulate what happens if you change things, but also what happens if external factors change. And then ultimately, you can also optimize your budget, and this is where the rubber hits the road, so to speak, because this enables so-called prescriptive analytics. This is where we can give prescriptive output that immediately translates to better KPIs. And then finally, as promised, talk about the data needs. There are really two big classes of data sets that we need. One is, and it's all historical, we need at least a full year of data on a weekly granularity, meaning 52 data points, right? But 2 years is even better because then you can capture certain seasonal effects. And this historical length applies for both sets of data. One is investments into marketing. So historically, we need to know what has been invested into the different types of marketing or advertising, such as paid search, display ads, TV, offline, online sales, you name it, as well as any other variables that we might want to capture. And then the second type of data set in orange, this is transactional data sets. We need to know simply for the corresponding weeks historically how much was sold on a product level at any geography or point of sales. And that's really it. And the machine learning algorithms, what they do is find the relationship between these two sets of data, outlining causality and then controlling for any other variables as well. This is the gist of it. Just in interest of time, I'm going to skip to the next use case, but feel free to post any questions. So the next use case, very similarly framed, is around price and discount optimization. This is also a very popular use case. Sorry, and I just see a question, so I might answer that if that's okay. How does model handle duplicative reach? Yes, thanks, Glenn, for the question. This is relating to what happens if, let's say, a customer is actually influenced by multiple instruments, marketing, multiple channels, not just one. How can we attribute the effect to one or the other, if I'm understanding the question right? To actually isolate the impact of a single channel, if multiple channels are actually influencing or driving sales, you need to augment the methodology with what's called attribution analysis. And to do that, you need even more data. The short answer is that this methodology as it is doesn't really capture the isolated impact per se, but if you have good enough models, it will tell you that just by investing in paid social, this is the impact you're going to get. That also controls for any effect that's kind of trickling down from different channels. But to do it 100% correctly and really identify what is the multiple effect, you would need different types of data that's currently only available in the so-called Clickstream Data sets. That means that for individual customers, you can really see their touch points, the journey they have taken before making a purchase. So, across a time series layout, you can see how many marketing channels actually influence their purchasing behavior. That data set is very elusive, and in this example, it's not incorporated. If the data is there, that's great, but most of the time, it's very hard to get hold of, so that's why it's not included in this example. This is a good time to say that no model is perfect, but most are useful. So there's infinite ways to make a model better. It all boils down to what data sets you have available. Hopefully that answered the question.
Yeah. Along those lines, Robert, there's another quick question that came in. How do you predict for abnormalities like COVID disruption in your data set?
Great question again. It boils down to what kind of so-called variables you define in your model. In this example, we focused on the marketing investment. So imagine the dollar amount invested into Facebook media on a weekly level, looking back for the last 2 weeks, is a variable. Don't want to get too technical. And with that variable, the machine learning algorithm picks up on the relationship between it and the KPI that we're trying to predict, meaning sales. But you can define any variable that you like, right? As long as, again, if you remember the methodology slide, if we assume that it influences sales, such as the COVID indicator. And also in this example, we actually defined those variables. So we do control for COVID deaths or number of cases, depending on how you want to express the variable. It's just that we're not exposing it as a simulation variable in this case. We're just saying that, well, we're controlling it. We're putting a value of X on top of it. Let's say we're expecting COVID to stay the same as 3 months ago. controlling for that, how does Facebook investments alone impact your marketing spend? But you can take it a step further and say, well, what if I want to simulate what happens with how COVID changes impact my sales? There's no technical reason why you can do that. It really boils down to, if I can go a few slides back, it really boils down to predictions, simulations, and optimizations. And then you can simulate what happens if COVID takes a turn for the worst. But if you don't want to do that, you can just express it as a variable and then simulate other variables such as media spend while controlling for that value. Let me know if this was too convoluted of an explanation. The short answer is that absolutely you can and you should control for these external variables if you do the machine learning models correctly. Moving on to price and discount optimization. This is another very frequent use case in CPG and in other industries, as a matter of fact. Problem, as you can guess from the name, ineffective price reductions lead to losing market share. This is, again, a Fortune 500 brand. The approach, very similar, don't want to repeat myself. It's really based on machine learning algorithms in the context of predictions, simulations, and optimizations. The impact here was a 15% increase in revenue year over year, and again, a single source of truth enabling pricing teams to come together and align. The same type of framework again. If you do machine learning algorithms right, and I'm avoiding the term AI because we established that it's really machine learning under the hood, and if you open up machine learning, it's some class of models, distinct that is deep learning, but there are many more rudimentary ones that are applied, such as regression and all that. Don't want to confuse with buzzwords. It's just that I'm going to use machine learning as shorthand for the technical approach that we're taking. Predicting, simulating, and optimization, this is really the three things that are enabled by machine learning. In this case, we predict sales as a function of price point. What happens if we change price points either by changing the base price, list price, or the discounts. If we do that, then we're already in simulation territory. We can simulate real time, and then most importantly, we can optimize the prices or discounts for any group of SKUs in an ongoing manner. The methodology, you might see the same framework as before, but we are highlighting now a different column. This is because the pricing and promo related variables in this sense are the most important, but that doesn't mean we're not controlling for other factors, such as, again, seasonal, competitor, economic, and pandemic in the external bucket. The methodology here is relying on the demand curve. That's the most important thing because we are predicting the relationship between price and the demand. This is classic microeconomics. But we're also putting in some heuristics because you need to infuse business sense with the machine learning output. The two common elements here are price ladders. This is part of the price architecture that sets a specific brand in terms of how they price their products relative to other brands in the portfolio at normal price, discounted price, and undiscounted price. Sorry, at average price. And then similarly, the price spec curve is also another component of the price architecture. This just shows how, as you increase the size of your product, you get unit discounts. The orange boxes are here human-fed inputs, and then the blue box, the demand curve, this is the output from the prediction itself, from the machine learning predictions. And a workflow, this is just one way to illustrate it, again, using an application, a UI, but it's definitely not mandatory. It just captures all the moving parts that you as a business user would need to get value from a price optimization system. Not sure how much of this is actually visible. The idea is that for any list of products defined in the middle section, and just remember I have an arrow here, so each row represents one particular SKU, and this can be any list of SKUs, you can automatically find the optimal discount, as shown in the right-hand section. You can also simulate what happens if, for the entire group of products, you change the discount from any number of from 0 all the way to 30 or even 50%. And then in the bottom section, you can visualize the relationship between increasing discounts and your incremental revenue and your units, as well as your ROI. I just realized I failed to include an optimization panel, but it works in a very similar way as we have seen before. By hitting the optimize button, we need to establish, okay, what is actually the KPI that we want to maximize, let's say incremental revenue. What is the constraint? In this case, what is the maximum amount of discount we want to give? Let's say 50%. And as we give these parameters, the machine learning models can calculate what is the average across all your group of products. In this case, we have just 2, but imagine hundreds of products. And it can give you what is the best discount to give across the board that will maximize the revenues. So imagine a dot right here, which is the maximum of the incremental revenue curve. And this is very useful to optimize prices at bulk, especially for manufacturers selling in an online setting. And this can be done dynamically, so week by week, or even day by day, assuming, of course, that you have corresponding data in the back end. Moving on then to the data needs, but happy to come back here. It's a simpler data requirement because you really have just a single set of data that is widely available, well, to retailers at least, but also to manufacturers through syndicated data providers or any other direct channels. In this example, this was an online sales channel, so data was a bit more abundant, but the same structure can be found relatively easily, which is just all about historical transaction data on a weekly level, by SKU level, and getting some financial information such as list price, discounts, and the KPIs like unit sales and revenue associated with that. I'm going to pause here if there are any questions before I move to the third and final use case. Okay. Moving on, we mentioned behavioral segmentation as being the third use case that is interesting and definitely very prone to creating value through machine learning algorithms. And behavioral segmentation is a wide term in itself. This is all about segmenting customers through some sort of behavioral lens. A classic example of this, just to sidetrack a bit, is churn, right? What are the customers that are more likely to churn or others? That's also a form of segmentation. The other one is the famous recency, frequency, and monetary. You segment customers by how recent, how frequent, and how much value they shop at you with your brand. These are the classical ways to do segmentation. I want to show you a bit of a more interesting way to use segmentation called customer decision trees. The problem here that this gives an answer for is understanding how customers actually navigate the product category, and more specifically, what product features matter to the customers, what is driving loyalty, and which products are viewed as substitutes. This is a very loaded problem statement because underneath it, there are questions related to how should I optimize the assortment? Are there redundancies on the shelf, meaning that same products actually compete for the same consumer needs? The inverse of this, are there white spaces in the assortment? Are there some products that customers would shop but my brand is not offering? And it can also help more high level with marketing. How should I position my product so it resonates with what is important to the customer? Same approach applies. Machine learning algorithms segmenting the product categories by their features to reflect the needs and wants of the customer. In this case, we're only talking about a prototype, just a disclaimer that this was not yet launched in production at any company, although it's in the works. However, in my previous roles, especially at McKinsey, we did a ton of these projects using slightly different methodology, but the impact was very similar. So a solution is a simplified version here, is really to understand a few things, to enable the customer to understand a few things. Note that this is not about predicting, simulating, and optimizing anymore, because those capabilities can come on top of the CDT. So CDT is just more of a static segmentation that is created using a slightly different class of machine learning algorithms, and on top of which you can build further predicting and optimize capabilities. Super confusing, I know. But what does the CDT actually enable? It enables the user to understand a few things. What is substitutable versus complementary in the product category? What are the competitive sets? What are the loyalty drivers? And as mentioned, what are the white spaces and redundancies? I'm going to talk briefly about the methodology. It's actually a complex set of things that you need to go through, starting with shopper cart data. Knowing repeat purchase patterns is important, and applying different types of algorithms at different stages. Just going to throw one word out that some of you might be familiar with, the so-called dendrogram. That's a precursor to the customer decision tree. A dendrogram becomes a customer decision tree when the nodes of the tree actually get labeled with meaningful words. So let's jump straight into how to actually interpret what is a customer decision tree. This is a Tableau online visual. Again, any way you want to visualize the output, that's fine. It's just easier to do it in a user interface. This is a snapshot of an actual customer decision tree in the category of refrigerated juices and functional beverages in total US. And the nodes coming from top down represent really what type of features of the product category are important to customers. Features are basically whatever characterize the product category. In this case, since it's refrigerated juices, the first category, the first set of attributes that really matter is about whether the product is a conventional product or non-conventional. Non-conventional products usually have some health benefits or have recently been launched in the market. So this tells us that the first thing customers care about in that product category is this feature, meaning that shoppers who want to buy conventional products are not likely to switch to non-conventional products. And as we go down, we see that the second layer here is the manufacturer of the juices. And here a few things are interesting. One is that we can see the big players such as Coca-Cola and Pepsi, but we can also see a very niche player like Turkey Hill. And what this tells us is that, yes, Pepsi and Cola are there as distinct nodes because it means that customers who care about one prefer to buy within that manufacturer. And it also tells us that Turkey Hill has some unique features, some unique benefits and promises that are attractive to customers. And despite their relatively small size, so the size of the bubble indicates the revenue they generate, they have a distinct place in the minds of the customer versus the all other segments here. That means just a generic combination of manufacturers. So this tells us two things, that yes, after whether if it's a conventional or non-conventional product, the second thing customers care about is the manufacturer, meaning that manufacturer drives loyalty. The big brands are represented, meaning that they already carved the space out in the minds of the customer and have some loyalty. And in this sense, it's surprising that Turkey Hill, despite its small size, also has a place. So if I'm advising Turkey Hill, I would say, okay, keep it up. You're doing something great. You're differentiating your products. Let's see how we can capitalize on that. And if I'm advising Coke, I would say, well, how can we steal some share from Turkey Hill? What makes them so special? How can we either position the products to appeal also to Turkey Hill buyers, or how can we put products on the shelf which best resemble the offering that Turkey Hill already brings. And so on and so on. As we move down the levels, the uniqueness that each of these groups actually diminishes until it actually doesn't make sense to differentiate anymore. And therefore, the bottom section of the customer decision tree is where the competitive sets are defined. So this is the most granular way you can define a competitive set. Let's take a good example. So, Citrus World, for example, is also a manufacturer which is relatively small but also has some loyalty. So a good way to define a competitive set is that in a conventional segment, citrus manufacturer and GMO type of products. It means that customers who shop in this are not likely going to switch to anything else. Meaning if you have 10 products here and you take the favorite product of someone off the shelf, they're likely going to choose from the 9 remaining ones, not switch to anything else in the competitive set. This can deserve a whole lecture in itself, so I wouldn't go too much into the depth of the explanation. Maybe just a few more words on this visual, which is a different illustration of the same thing. This is just a horizontal layout that shows additional metrics associated with the nodes and the competitive sets. These are predictions in themselves, and this is where the predict, simulate, optimize capability can be tied back. We can predict what is the share of products versus the share of number of products, the share of products in a group versus the share of revenue. For example, here we can see that the share of products is 67% versus the share of revenue is 26%. That means that they're not bringing their fair share. And we can also predict growth and overall value of the node. And then finally, to make this complete, what are the data needs to fuel a customer decision tree? 2 sets of data. One is the retailer syndicated data that many manufacturers are familiar with. And the second is repeat transactions of known customers, either through loyalty cards or anonymized bank cards, or there are actually other alternatives now available, at least in the online space. Again, 2 years worth of history is recommended on a weekly granularity. So I realize I'm at the 46-minute mark, so would pause here, conscious that a lot of the information has been viewed. Happy to take some questions.
Sure, Robert. We have one question that came in, very interesting one. If you had to pick, what is the one use case that you would advise CPG companies to use AI for?
Mm-hmm. Thanks. That's a great question. Often when companies are contemplating whether or not to get on the AI train, they want to choose a use case because that's what really drives everything. I would actually advise on pricing and related use cases. You can just look at discounts, or you can look at promotions. That wasn't covered here, but it's a very similar methodology. And why? Because many studies have confirmed that pricing is the best lever to move the needle really in the short term. I believe there was a McKinsey study that said that 1 percentage point change in a price point in the right direction can translate into 5 percentage points increase in revenues. So that's an interesting fact to keep in mind. So on one hand, it moves the needle quite significantly, and on the other, the data needs to achieve the use case via machine learning is relatively simple. If you recall, we only had a single table as a data need versus at least 2 sets for the other use cases. So pricing and discount would be my recommendation.
Okay, one quick one, Robert. How do you use the last 2 years of data to predict into the future, since the last 2 years were not normal?
Yeah, that's a great question. We're always at the mercy of historical data, right? So without historical data, you cannot really predict that, the fundamentals of machine learning. And if the 2 years of data were like so disruptive that none of it applies for the future, then obviously we're in trouble. The good news is that it's never that black and white, even though there have been massive disruptions in some elements. So for example, in the macroeconomic space, driven by COVID and supply chain difficulties, other fundamentals are relatively intact. So for example, the demand for products that are driven by pricing or driven by distribution, promotion, and marketing. And if the machine learning model is set up right, it can capture those effects and then use them to make the predictions while signaling that the error rate is not, but while signaling some information about how you can actually improve the model by incorporating other variables. So the short answer is that you can always create models that tell parts of the picture with great accuracy at the expense of not being able to tell the whole picture. But being able to tell part of the picture can in itself be used for increasing business performance, such as pricing and marketing investments.
Okay, well, thank you, Robert. For more information about this topic, you can contact Robert at robert.molnar@wqpredictive.com. Thank you, Robert. That was excellent. A nice simplified explanation of a complex subject. I appreciate it. Thank you very much.
Thank you for your time.